Welcome to the chapter on mechanical design. Mechanical design is a crucial aspect of mechanical engineering that involves creating components and systems to meet specific requirements. This chapter will cover the fundamental principles of mechanical design, including design principles, stress and strain, and fatigue and fracture. Design principles are the foundational guidelines that engineers follow to create efficient, reliable, and cost-effective mechanical systems. Key design principles include functionality, ensuring the design meets the intended purpose and requirements; safety, incorporating features that protect users and operators from harm; reliability, designing components to perform consistently under expected conditions; economy, balancing cost with performance and quality; and sustainability, considering environmental impact and resource efficiency. When designing a bicycle frame, engineers must consider factors such as weight, strength, and durability. The frame must be lightweight for ease of use, strong enough to support the rider's weight, and durable to withstand various riding conditions. Materials like aluminum and carbon fiber are commonly used due to their favorable strength-to-weight ratios. Stress and strain are fundamental concepts in mechanical design that describe how materials deform under load. Stress is the internal force per unit area within a material, while strain is the measure of deformation representing the displacement between particles in the material body. Stress, denoted by the Greek letter sigma, is calculated using the formula sigma equals F divided by A, where F is the applied force and A is the cross-sectional area. This formula helps determine the internal force per unit area within a material. Strain, denoted by the Greek letter epsilon, is calculated using the formula epsilon equals delta L divided by L0, where delta L is the change in length and L0 is the original length. This formula measures the deformation representing the displacement between particles in the material body. In a tensile test, a sample material is subjected to a pulling force until it breaks. The stress and strain are recorded throughout the test to create a stress-strain curve, which provides valuable information about the material's mechanical properties, such as the yield strength, ultimate tensile strength, and Young's modulus. Fatigue and fracture are critical considerations in mechanical design, especially for components subjected to cyclic loading. Fatigue is the weakening of a material caused by repeatedly applied loads, while fracture is the separation of a material into two or more pieces under stress. Fatigue is the weakening of a material caused by repeatedly applied loads. Even if the stress is below the material's yield strength, repeated loading can lead to the initiation and growth of cracks, eventually causing failure. The number of cycles to failure can be represented by an SN curve, which plots stress versus the number of cycles. Aircraft wings experience cyclic loading during takeoff, flight, and landing. Engineers must design the wings to withstand these repeated loads without failing. This involves selecting materials with high fatigue resistance and incorporating design features that minimize stress concentrations. Fracture is the separation of a material into two or more pieces under stress. It can occur due to a single application of a high load, known as brittle fracture, or the growth of cracks over time, known as ductile fracture. The study of fracture mechanics helps engineers predict and prevent catastrophic failures. Pressure vessels, such as those used in chemical plants, must be designed to prevent fracture. Engineers use fracture mechanics to determine the critical crack size and ensure that the vessel can operate safely under high pressure. Understanding the principles of mechanical design, stress and strain, and fatigue and fracture is essential for creating reliable and efficient mechanical systems. By applying these concepts, engineers can design components that meet functional requirements, ensure safety, and achieve long-term performance. Thank you for watching this chapter on mechanical design. We hope you found it informative and helpful.